It's 3 o'clock. We have an amazing presentation here. We saved the best for last. An incredible build-up. No, seriously, if you walk into the museum today through the normal door, you walk past his work. This is Charles Anthony. He spent a long time bringing us to DPS8M, the emulator, and then a slightly longer time, or lesser time, getting it hooked up to a front panel and reanimating it. So, Charles?
My name is Charles Anthony. I'm going to talk about what I've been doing for the last 4 years, bringing the Multics operating system back to life. The DPS8M Emulator project is an open source collaboration with the aim of creating the emulation of the DPS8M mainframe and mainframe computer and running the Multics operating system on it. I'm going to briefly cover the history of Multics, the DPS8M mainframe and emulators, and then go into detail about the emulator project and my history with it. It's going to be deeply technical and deeply personal. The project has been my passion for the last 4 years with victories and defeats. The thrill of shipping release 1.0, the agony of intractable bugs. Multics timeline. In 1965, Project Mac, Bell Labs, and GE formed a joint project to create a time-sharing operating system, Multics, Multiplex Information and Computing Service. In 1967, Multics boots in single process mode. A few months later, multiple processes were running. Then gross discrepancies between actual and expected performance of the various logical execution paths throughout the software led to an unanticipated phase of design iterations. In 1969, a GE645 Multics was delivered to MIT and runs a time-sharing service. In the same time frame, Bell drops out of the Multics project, and Unix starts development. After 19 years, MIT shuts down the Multics system. Last release of Multics, MR 12.5, was in 1992. In 2000, the Canadian Department of National Defense shuts down DNDH, the last running Multics system. Hardware timeline. Multics needed hardware support that did not exist at that time. Computer makers were solicited for proposals to provide systems with that support. In the early 60s, General Electric was shipping the GE635 computer and successfully bid a proposed extension of the 635 to meet the needs, the GE645. The principal difference was the addition of the append unit, what we would now call virtual memory. What was more than that, not just paging and virtual addressing, but also hardware supported rings and segments and security and capabilities they provided. In January 1957, the first 645 was delivered to the Multics developers late. In 1970, Honeywell purchased the General Electric Large Computer Systems division. The 635 continues on as the Honeywell 6080, and the 645 has improvements made and becomes the 6180, shipped in 1973. A 2-CPU system with 768 kilowords of memory, 8 megabytes of bulk store, 1.6 gigabytes of disk, 8 tape drives, and 2 DN355 serial line controllers, similar to MIT's system, had a purchase price of about $7 billion, $38 million adjusted for inflation. Improvements in semiconductor technology led to the DPS8M, shipped in 1979. Larger capacity memory units allowed the reduction in the number of memory controller connectors from 8 to 4. The blinking light maintenance panels were replaced with a mini computer-based diagnostic system, and increased component density led to smaller, more power-efficient systems. The Multics operating system. The process address space is divided into segments, each segment with its own access controls, and the segmented address space is virtual with command paging. The bulk of the operating system is implemented in PL1. The hardware allows 8 CPU symmetric multiprocessing. PL1 assembly, COBOL, Fortran, VCPL, DBL Basic, MacList, Pascal C, and the first commercial relational database. Multics was the first to provide a hierarchical file system. In addition, access controls in individual files, long names, multiple names, symbolic links, storage quotas, removable devices, mandatory access controls. Multics introduced the idea of treating all devices uniformly as special files. It was the first OS to run on a symmetric multiprocessor, and the only general purpose system ever rewarded a V2 security rating by the NSA. Security designed in from the beginning and enforced in hardware. Online reconfiguration. CPUs, memory units, I/O controllers, and peripherals could be added or removed from running systems. Several large sites were their systems during off-peak hours by removing the CPU, a memory controller, and an I/O controller from the running production system, recabling those modules and booting customers in Multics, and reversing the process at the return of peak hours without interrupting the production system. Dynamic linking is the norm. Typically, executables only be statically bound when they're installed in production environments. Command language, a shell of search rules, I/O redirection, working directories. Multics did it first. The problem, Multics only ran on this hardware. There were about 100 installations and none of them remained. Port Multics to a modern architecture? Multics was never intended to be portable. The 36-bitness of the architecture, the source of PL1, and full of word-size dependencies, lack of anything resembling the segments and rings of the native hardware in modern architecture makes this a daunting task. That leaves the emulator route. What could go wrong? Mulch hardware is a modular design, each module taking up 1 or 2 full-size cabinets. The CPUs run about 1 MIP. Instructions were 36-bit wide with an 18-bit operand, allowing a segment size of 256,000 words. Segment numbers were 15 bits, allowing 32,000 segments, or theoretical 8 gigabytes of address space per process. Multics table sizes and backing store sizes, so there's a much smaller limit on that. 2 36-bit accumulators, A and Q, 8 18-bit index registers, 8 pointer address registers, each containing a 15-bit segment number, 18-bit address, and 6-bit number. An elaborate indirect addressing scheme allowing chained indirection, tally decrements, and address increments, register indexing, segment crossing. An interesting side note, the no operation instruction includes an operand address and address preparations performed, which includes walking the indirection chain. This means that the no op instruction can alter memory, page fault, and incur access violations. The CPU does 36 and 72-bit integer and floating point arithmetic, 10-digit decimal arithmetic, string move and compare, decimal number formatting, as in COBOL and PL1 PIC. The CPU operates in 2 modes: absolute mode with memory access to the lower 256K of memory, and privileged instructions depend mode with segmented memory access. Physical memory addresses are 24 bits, allowing 16 megawords of physical memory. Memory is contained in the SU modules. Late model SUs contain up to 4 megawords of memory, meaning 4 SUs are needed for a full memory system. The I/O controllers were attached to the SUs. All I/O is DMA. The CPU had only a single I/O command, connect to I/O controller, with an operand specifying which I/O controller to signal. The I/O controllers send interrupt signals to the SCUs. They contain the logic and mask registers that control the forwarding of the interrupt to a particular CPU. The FMVs manage serial communication lines, asynchronous bisync X25. Depending on model configuration, up to 96 high-speed asynchronous lines could be managed. 8 FMVs were allowed, so potentially 768 dial-up lines per system. Multics terminology. Segments are central to both the hardware and Multics, but are semantically different between the two, which confused me no end for a while. To the hardware, segment is an entry in a segment descriptor table indexed by 15-bit segment number. The entry is a page count and list of 1,024-word pages comprising the 120K word segment address space. For each page listed a page present bit, a page modified bit, and a page line 24-bit physical address. Virtual memory unit with an extra level for segment indexing. CPU has a process segment register containing the segment number of the current process and the temporary segment register used when referencing out a segment. The pointer registers each include a segment number field, and indirect addresses may include a segment number field. Multics defines segments as named persistent storage. The process of initiating maps a named segment into the process address space by assigning the segment number to it, somewhat analogous to a DLL load, returning the address of the library that it was loaded at. Rings are part of the Multics security structure. The innermost code, interrupt handlers, process scheduler, resource allocation, runs in ring 0. Multics code that does not need privileged hardware access in ring 1, user processes in ring 4, limited access processes in ring 5. Each segment has ring bracket registers that control read, write, execute access from the specified ranges of rings. This access is evaluated by the hardware. When an address crosses rings, violations are rejected. Pieces. What resources were available to the emulator writers? VCF provided a treasure trove of documentation, the most important pieces being the Multics Processor Manual, Multics Differences Manual, Hardware Software Formats, Programming Logic Manual, and the 6000B Engineering Product Specification 1. The Multics Processor Manual, known as AL39, defines machine language, the instruction set, registers, addressing modes, virtual memory, mostly. The Differences Manual describes the changes for the level 68 to DPS8 transition and provides insight into the underlying structure of the system. Hardware Software Formats Manual defines the bit layout of many of the registers and data transfer words with a all too brief definition of the bits. The I/O Multiplexer Manual defines the I/O controller and its interface to the SGU and the channel controllers, again, mostly. The GE605 computer that the Multics hardware was evolved from continued on as the Honeywell 6080, level 66, DPS8, and eventually is the NovaScale 9000 emulator, which is an active commercial product today, running legacy GCOS applications. Gold publishes RJ78 NovaScale 9000 assembly, which describes a machine that's a close cousin of the DPS8M and was uncovering some of the missing detail in AL39. And Multition. Quote, anyone who contributed to the development and success of Multics, there is no such thing as an ex-Multician. The Multician.org website presents the story of the Multics operating system for people interested in the system's history, especially Multicians. The site's goals are to preserve the technical ideas and advances of Multics so others don't need to reinvent them, record the history of Multics, its builders, and its users before we all forget, give credit where it's due for important innovations, remember some good times with good people. Multicians.org also runs a mailing list, which they kindly allowed Harry Reid and I to join and ask stupid questions on, providing access to the people who really know what's going on. I was recently speaking to a Multician who vouchsafed that the Multicians had discussed the possibility of an emulator and come to the conclusion that it was an impossible project and that we were not expected to succeed. Overview of the emulation history. In 2007, Orange Squid created a source for it project, last updated in 2010. Basically, 6-bit arithmetic functions implemented, no pen unit or tape I/O. In late 2007, Vol released the source to Multics, released 12.3 and the 12.5 update. With the sources, writing an emulator that could run Multics became feasible. Multics was no longer an arbitrary string of bits. When an emulator bug caused the Multics malfunction, it would be possible to understand what Multics was trying to accomplish at that point, and from that, an understanding what the emulator did wrong, hopefully with a reasonable amount of effort. In early 2008, Michael Mondi created the GitHub Multics ML project and worked on it through 2012. The code successfully reads the root tape record, the first stage bootloader, and early portions of the boot code, completing about 2 million emulated instructions. The emulation fails at the first page fault. The fault handling was not completed. Quoting Mr. Mondi, I started from a new code base. However, I would not have attempted to write this without having the foundation led by the Multics community. The programming isn't that hard. The hard part is getting specifications and descriptions and figuring out what the hardware is really supposed to do. In particular, discussions of the boot process, a working boot tape and source of boot code are so invaluable that I would not want to try this without them. Doing an IOM without having the boot tape as a sort of behavioral description would be impossible. Mr. Mondi adopted the SimH emulator framework, an excellent platform developing emulators on. It provides a debugging tool set, event scheduling, extensible control, configuration interpreter, serial port emulation, platform portability, and much more. In 2013, Harry Reid created the source board project DPS8M, uploading work that he started in 2012. From the project source code page, hello all. Well, as you may have guessed, another hapless individual has begun the task of resurrecting Multics. Granted, several others of more capability and valor than myself had attempted to create a simulator for the DPS8M and have run screaming from the mere complexity of the task. I have nevertheless decided to go where angels fear to tread and attempt to write a SimH-based simulator capable of using Multics. He merged much of Monde's code base, but completely re-architected the emulated CPU code to better follow the hardware architecture. He also wrote a process assembler enabling the creation of DPS8 assembly language unit tests and started building FXE, the full execution environment, wherein Multics applications could be run in the emulator with FXE servicing the application system calls, making the application believe that Multics is running, somewhat akin to wine. November 9th, 2014, a hello world program is typed in, compiled, and run. Shortly after this, the first alpha release was pushed out, single user mode only. Looked at it cross-eyed and it crashed, and many, many things that just did not work, but a release. On December 10th, 2014, Multician Olin Siebert was moderating the Distinguished Practitioner panel at the Applied Computer Security Applications Conference. He took the opportunity to demonstrate the DPS8 emulator to an audience of about 400 computer security professionals and students. In late 2016, another team fixed a small number of Multics Y2K issues and generated Multics release 12.6. In August 27, version 1.0 of the emulator was released. Sometime in late 2013, I was searching the web looking for a PL1 compiler for some project that I have long forgotten about. Multics had a PL1 compiler, and if the emulator were made to work, I would have a PL1 compiler. Although I had no DPS8M or Multics experience, I did have a lot of frame experience, CDC 6000, IBM 360, and had written or worked on several emulators over the years. I took a look at the code in the AL39 and thought that, yeah, a couple months, no problem. Let's get this puppy right into shape. Right. At that time, the emulator was capable of executing the first few hundred boot tape instructions. We would look at the bootloader source code, AL39, emulator instruction sets, figure out what went wrong, fix the emulator, repeat. By early 2014, it was beginning to dawn on me that there was a fundamental problem. We had enough documentation to make the project possible, but so much information was missing that it was going to be very, very hard. Harry was making good progress on the CPU instruction set. I had experience in device drivers, so I tackled the I/O controller, IOM, emulation. The code had a lot of just for now bits in it, many of which dealt with the lighting, unit numbers, and configuration concerns. I started chasing them down and realizing that we needed to be able to model the modular nature of the hardware. Added the cable command to SimH, emulating the physical cable interconnections. This allowed the specification of what module connects to what module and which ports. The current release has about 80 cable commands in the default configuration. Harry became quite irritated with me when his code stopped working, but forgave me when he read my check-in log note. IOM now working well enough that correct configuration matters. The IOM could read the tape and interact with the operator console for any channel assignments or IOM unit numbers. But this would not be the last time I was in the IOM code. Looking over the Git log, February 2014. Radio rewrite, try number 3. June 2014, radio write, try number 4. Try number 4. Try number 5. Page support, rewrite IOM. The IOMB page support was pretty special for me. Multics was passing channel control programs to the IOM that the IOM was unable to parse. There were bits set in the channel program that were defined to be 0. Perplexed, I was rereading the IOM EPS1 from top to bottom over and over again, trying to suss out what was going on, or some definition of bottom. It dawned on me that Appendix 1 of the document was not, as I thought, describing an irrelevant late model functionality, but rather the functionality that Multics was expecting. Appendix 1 described extensive modifications to the IOM to allow it to access the page tables of the CPU, enabling the I/O to the processes at address space as well as kernel space. So a couple hundred more lines of code, and the IOM was working. Computed address formation is the operand address preparation phase of instruction execution, covering about 23 pages of the AL39 manual. CAF is driven by an 18-bit operand address, a 1-bit user pointer register flag, and a 6-bit address modification field. 6-bit tag gives 32 possible addressing modes. I'm not going to go over these. I just want to make it clear that operand address calculation is complex and convoluted. The important bits are that the length of the descriptor chain is unbounded, and that processing of the descriptor can have side effects, modifying address and tally fields. This makes page fault handling problematic, as is the case where an indirection chain includes the increment address, decrement tally, and continuing descriptor, and a later descriptor causes a page fault. On instruction restart, the address preparation cannot start from the original address, as that would cause the increment and decrement cycle to be repeated, resulting in incorrect address calculation. Frustratingly, the interaction of page faulting is completely elided in AL39, but it's absolutely critical to cooperation. AL39 spends only 6 pages on the address modification field, so details are a bit thin on the ground. For example, the IT mod flowchart contains a node with this helpful gem. I think I know what that does now, but I don't know. The computed address formation code is running about 1,600 lines of C. I'm still not convinced it handles all restarts or segment crossings correctly. Harry and I spent many months debating the edge cases and stomping over each other's changes. This code probably brought us as close to dysfunction as we ever got. The outstanding fundamental implementation issue revolves around the interaction of computed address formation and virtual address processing. Virtual address processing is done by the append unit. It is a state machine. It has statements like, was the last cycle an indirect word fetch? This means correctly invoking the append unit is as important as its correct implementation, yet the invocation is completely undocumented. When computed address formation is updating address and tally field, what cycle type should it use? Using the incorrect cycle type could cause the append unit to reset the segment number, causing the operand to address the wrong segment. We have reverse engineered cycle usage by tinkering with it until Multics runs, but I'm sure there exists untested code paths that are just wrong. AL39 states there are 3 modes of main memory addressing: absolute mode, append mode, and bar mode. It lies, there are 4. Bar mode is base and boundary location, a region of memory starting at address base of length bound is treated as if it starts at address 0. Append mode is segment addressing. Addresses are composed of a 15-bit segment number and 18-bit offset in the segment. Append mode and bar mode are independent, so 4 modes: absolute bar, append, and append bar. An append bar, a region of memory in the segment, is treated as if it starts at offset 0 in the segment. Multics includes the GTSS subsystem, a GCOS simulator that allows GCOS applications to run under Multics without recompilation. GCOS applications run in bar mode on the 635, so to enable the simulation, GTS runs the application in a segment with bar mode enabled. Getting this to work in the emulator when the 3 modes meme of AL39 was present from the beginning caused a lot of grief. The CPU maintains an 18-bit instruction counter and a PSR register containing the 15-bit segment number. In absolute mode, not appending, not bar, instruction addresses are 18 bits and address the lower 256K memory. In append mode, the 18-bit address and the 15-bit segment number are used to look up the 24-bit address in the in page tables. By late December 2014, I was becoming aware that CPU design was not capable of correctly managing page faults. The ability to restore the CPU state, allowing the instruction to resume where they left off after the fault was serviced, was just not feasible. As an example, the code that implemented the XEC and XED instructions interpret the instruction as an instruction, interpret the operand as an instruction or instruction pair and execute it, was implemented as a recursive call into the instruction execution routine. If the operand instruction execution encountered a restartable fault, there was no way to track that recursion in the available fault data space. I rewrote the CPU as a state machine. leading to a long period of loss of functionality and stability. I fixed a bug in that code as recently as September 2017. The implementation has evolved. Currently, the states are instruction fetch, execute, fault execute, interrupt, interrupt execute, and fault return. The emulator CPU state machine has a set jump as its entry to the state switch logic. Access violations and page faults are implemented as long jumps back to the state machine rather than passing a fault return code back up the call chain. The fault data space is an 8-word data structure that is saved by a fault or interrupt and used to restore the CPU state that it was when the fault occurred. The state data includes the two-word instruction working buffer, which contains the instruction pair that was being executed at the time of fault. It also contains a handful of bits about the execute instruction, execute double instruction, instruction state. These instructions load the operands into the instruction working buffer, overriding the XCC or XCD instruction to be executed, and sets various CPU control bits indicating that an XCC or XCD is in progress. When the instruction is restarted, these bits are restored, allowing the CPU to correctly continue the execution sequence. There are also bits in the data structure indicating repeat instruction state, interrupt fault flag, interrupt number, 24 fault status bits, append unit state, computed address formation state. The XSF flag. There's only one reference to this flag in the documentation and multi source, and no definition. Again, the definitive documentation of the data has led to much heartache. One would hope that as long as the save and restoring limitations are symmetrical in the emulator, that all be well. But Multic sometimes modifies the saved data before restarting the instruction, so there's little room for loose interpretation of the semantics. The XSF flag is particularly irksome. The documentation default data space says, word 0, bit 19, XSF, external segment flag. The strings XSF or external segment flag appear nowhere else in the documentation or Multic source code. From reading the Multic source code, it was deduced that the RFI bit, restart this instruction, was set by the operating system, not by the hardware, and was used to indicate the instruction was resumed where it left off or restarted from the beginning, in the opinion of the operating system. Another interesting oddity is the master mode entry instruction, apparently intended as an instruction used by applications to enter operating system, to make operating system requests. I knew them as trap instructions. They generate an MME fault. The operating system sources the fault, performs the indicated request, and returns to the application. Multic does not use the instructions, but GCOS, and therefore the GTSS GCOS simulator does. In every other architecture I've had experience with, the trap instruction resumes with the next instruction after the trap, analogous to a subroutine call instruction. On the DPS8M, the instruction resumes back to the same instruction that trapped. It's the operating system's responsibility to increment the return address and the fault address to perform return from trap functionality. The append unit is the heart of the Multic system. It is responsible for mapping virtual segment addresses to physical, tracking which segment is being addressed, triggering page faults, tracking page modification, verifying access rights. But we are not sure how it works. There's a 9-page flowchart of the append cycle attesting to its complexity. And a quick Google for VAX virtual memory flowchart turned up single-page flowcharts. Sadly, it is both incomplete and wrong, and I believe the emulator is still incorrect. An egregious typo was discovered recently. The incorrect ring register was being used for write permission checking. It turned out that memory write protection didn't actually work in the emulator. It was perfectly acceptable for user mode programs to write to any segment visible to it, including those belonging to the operating system. This typo is in every version of the append cycle flowchart that I can find in the manuals. Oops. The fundamental issue revolves around the append unit being a state machine. It is statements like, was the last cycle, an indirect word fetch. This means correctly invoking the append unit. It's important. Yet, invocation is completely undocumented. In addition, there are such items as this node in the flowchart. This is the only mention of APU data in the documentation. Again, we've managed to reverse engineer many of the details of the append unit by studying the Multic source code, consulting multicians, and tinkering with it from until Multics runs. BitSavers has a collection of Multics tape images consisting of 12.5 boot tape, the 12.3 release, the 12.5 update release, and a tape labeled T4D. We eventually worked out that T4D was a transcription error. It should have read T&D, or test and diagnostics. The multicians indicated this would be a standalone hardware diagnostic tape and highly encouraged focusing on getting that running. The tape turned out to contain a powerful and comprehensive diagnostic test suite. The first record on the tape is rootable, consists of an overlay loader. The overlay loader searches the tape for records containing a specified key value, loading and executing the record when found. The records contain tests, and when each test is finished, it uses overlay loader to start the next test. The first two tests rigorously and comprehensively test a handful of instructions. The remaining tests are written entirely in that small set of instructions, plus whatever instruction that particular test is covering. This technique gives a high degree of confidence to the test harness. If a particular test fails, it's almost certainly due to a problem with the target instruction rather than a failure in the test harness code. The first test covers the jump instruction. Does it jump to an even address correctly? Does it jump to an odd address correctly? Does it jump from odd to odd correctly? And so on. The test is implemented by jumping through a thicket of DIS star instructions. This is delay until interrupt signal instruction. It will cause the CPU to halt, and the address of the instruction will be displayed on the maintenance panel. If the jump instruction lands at the wrong place, it will hit the DIS instruction holding the test. The field engineer will read off the address from the maintenance panel, look up the address in the T&D documentation, and follow the troubleshooting procedure outlined there. We don't have a copy of the T&D documentation. We boot the tape in the emulator. It runs for a few thousand instructions, pulse in the address, which has no meaning. So the process becomes reverse engineering, disassemble the code around the address and try to figure out what it was doing and what result it expected but failed to achieve. Because the tests were written in a very small instruction test, many simple tasks, dozens or hundreds of instructions to accomplish, making comprehension of the test very hard. Eventually, we got the first 11 tests to run, with one exception. The 12th test reads and rewinds the tape endlessly. No one has ever been able to figure out what the problem is. If it's in the tape drive emulation, or if the tape image is incorrect, or something's wrong, who knows. The exercise was fruitful. There were many instructions that suffered from woefully incomplete documentation, and we now have high confidence in due to the T&D tape. The instruction we could never get right was the load indicator instruction. It loads the accumulator register with several computational state flags, such as 0, negative, carry, and overflow flags. It also loads the address mode bits, bar, and appending. AL39 says the LDI instructions should set bit 31 if the CPU is in absolute mode and off if it is in pending mode. Examination of the multi source code confirms this behavior, and other references in AL9 support this logic. The T&D tape tests the LDI instruction while running in absolute mode and checks if the bit is off and signals a failure because the emulator following AL39 sets it on. Examination of the symbol code showed a simple and straightforward test. The code was circulated among the multicians who agreed the code was doing the wrong thing, and no one could come up with a plausible explanation. We added a runtime configuration switch to the emulator, then inverted the sense of bit 31 so the T&D test could continue on, and shelved that problem until someone could think of a plausible solution. After several years, it dawned on us, wrong tape. Booting the T&D tape loads the first and then the third record of the tape. What is in the second record? Examination showed it to be a bootable record, quite similar to the first record, except that it wanted the absolute mode indicator bit to work as documented. It seems the first record is for testing CPUs without the append unit installed, the non-Multics enabled model that ran the GCOS operating system. To test the Multics CPU, skip the first record of the tape before booting. The different boot records will set configuration bits differently in the overlay loader, causing it to select those test records on the tape appropriate for the CPU board. Once the emulator is running well enough that Multics was bootable and stable, if not completely functional, we turn to isolates. The isolated online test subsystem is amazing. It is a rework of the T&D test for use in a running system. For sites with multiple CPUs and multiple SCUs, it was possible to run the tests on one of the CPUs while leaving Multics running on the remaining CPUs with no service interruption. When the field engineer runs isols, it takes the CPU to be tested offline, reserves the memory in one of the SCUs, reconfigures the test CPU to use that SCU as its low memory, installs test and diagnostic code in that memory, starts the test CPU running the test. It does this while Multics is still running on the remaining hardware. An impressive feat. Isols also has the benefits of a much more verbose and generally helpful diagnostic message that is often including the purpose of the test, the expected result, and the actual result. Unfortunately, Isols only runs in multiple CPU systems, and therefore the DPS emulator only supports a single CPU. Necessity calls. I had always wanted to support a multiple CPU emulation with threading of some kind, but I knew that taking code of this complexity and size to threads would be a major undertaking, especially if threading considerations had never been taken into account as part of the design. But I also knew that one of the first steps toward that would be reorganizing the emulator's data structures into a coherent whole, not the ad hoc massive accretion that was the case. I decided that if the data structures were properly marshaled, it would be possible to make it an array and do a round-robin implementation of multiple CPUs. Some rearranging and recoding later, I had multiple CPU ports that didn't work. It turns out the interrupt routing code was very broken for the case of one more CPU. That took a fair amount of reverse engineering and testing. Now we could run a multiple CPU Multics, albeit running slower proportionate to the number of CPUs. But the ability to run isols at all makes the cost irrelevant. Isols runs the primitive function test from the T&D tape to provide the test harness instruction set. Since that portion of the T&D tape was already proven, the emulator passed the PFTs with flying colors. However, upon passing the PFTs, isols displays hardware configuration data gleaned from the tests, including the CPU serial number. The instruction to retrieve the serial number is well documented, and Multics retrieves and displays the serial number correctly, but isols displays it gibberish for the serial number for some reason. Isols then runs about 90 test suites depending on the model and configuration of the CPU. Each test suite composed of several subtests. Each subtest deeply tests an instruction, exploring the corner cases, a tour de force of testing. It took a long time and a lot of code rewriting to get from being able to run isols to the point where we were happy with the isols results. The remaining isols failures are mostly due to implementation compromises and features that we decided not to implement. For example, the original hardware had a 512 kilohertz countdown timer used to schedule process switching. The emulator estimates time by counting instructions, sacrificing timer accuracy in exchange for significantly reduced overhead. And isols can detect that discrepancy. Also, the hardware supported interruption of long-running instructions for timer runouts or hardware interrupts. Since the single-threaded emulator handles interrupts synchronously, those long-running instructions are allowed to complete. And again, isols detects that. There are a couple of tests we have convinced ourselves that the instruction in your test is correct, and isols is misdiagnosing. It is unclear as to the calls. The speed bottleneck in the DPS8M hardware is main memory. It reads and writes a 72-bit double word at about 1 megahertz. In appending mode, an instruction fetch requires look up the segment descriptor segment page table, retrieve the segment descriptor from the descriptor segment page table, look up the page address in the segment page table, read or write the operand data at the address page. 4 memory cycles just to fetch the instruction. In order to deal with this, the segment descriptor and page table caches 16 entries deep on the 6180, 64 entries deep on the DPS8. By the time I had arrived, somebody had carefully coded slightly buggy and incorrect one-way instead of 4-way cache. At some point, even though I am aware of the dangers of premature optimization, I did an execution profile of the emulator to see if there were any obvious hotspots. Yeah, there was. The emulator was spending nearly 90% of the execution time searching the caches for entries that it could simply fetch directly from the blazingly fast memory of the host in less time than it took to check a single entry. Making a quick pass of the code, replacing every check of the cache with the assertion that the entry was not in the cache produced a 10 times speed up in the emulator. These caches were critical to the hardware performance, so ISOLs test them heavily. The cache code has been reinstated as the compile time conditional, and the four-way logic has been correctly included. There are 8 pointer registers and 8 address registers, but there are really 8 pointer address registers. Pointer registers have an 18-bit word number, 15-bit segment number, a 3-bit ring number, a 6-bit number that can specify any bit in any word in any segment. Address registers, 18-bit word number. Oh, that's a typo. A 6-bit number, word number field, and a 2-bit character number field, but no segment number. They can address any bit in any character in the current segment. The important difference is the way they number bits in a word. For the pointer register, the bits are number 0 through number 35, specified by 6-bit integer. For the address register, the word is divided into 4 9-bit characters, 0 through 3, specified by 2-bit integer, and a bit position in the character 0 through 8, specified by 4-bit integer. Either register can specify a particular bit, but with different notations. The L39 then gets a bit confusing. Because the multiprocessor was implemented as an enhancement to an existing design, certain apparent anomalies appear. One of these is the difference in handling of underlying data items by the appending unit and decimal unit. The decimal unit handles all underlying data items with a 9-bit number and a bit offset within the byte. Conversion from the description given in the EIS descriptor is done automatically by the hardware. The appending unit maintains compatibility with the early generations of the processor by handling all underlying data items with a bit offset, again with any necessary conversion done automatically by the hardware. Examples were found in the Multic source code that demonstrated that the address and pointer registers were the same registers. Places were found where a pointer register was set to 0 and the code assumed the corresponding address register had been set to 0. We concluded that the registers were the same bits, and the interpretation of 6 bits of the data offset varied between the appending unit and the decimal unit, and the emulator was coded to store the bit offset in the pointer register format. Those instructions that reference the address register would convert to and from character number. Multic seemed to run fine that way, but ISOLs complained mightily. Careful examination of the failing cases indicated that the solution was a bit more convoluted. ISOLs was carefully checking the conversion of bit offsets in the address registers, including illegal values. It would set the address register to character 0 bit 10. The emulator would convert this to bit 10 and store it in the pointer register. When ISOLs read back the register, the emulator would convert bit 10 to character 1 bit 1, which ISOLs considered incorrect. Reworking the code to save the bit offset in the character address format caused ISOLs to fail the pointer register test. More head scratching and waiting for the documentation led to the complex answer. The pointer and address registers are separate but synchronized. Setting a pointer register sets the corresponding address register and vice versa. Setting and reading the same register preserves the data. Reading the corresponding register retrieves the data that was changed to the appropriate format. Turn your AL39 to page 218 in the VSA absolute mode to absolute address to A register. That's summary we see final main memory address to A register. At notes we see if the ABSA instruction is executed in absolute mode, contents of the A register will be undefined, and attempted execution in normal or bar modes causes an illegal procedure fault. This doesn't seem to leave any modes the instruction actually works in. The T&D and ISOLs indicate that the L39 is just wrong. ABSA works in all modes, albeit with interesting differences between the results. Oh, we're not even leaving. I'm getting the talk faster call. So I'm going to skip to the slides for the other documentation highlights. Yeah. Story problems. Interpreting, parsing operator precedence in sentences works really different depending on where you put the implied parentheses. September, I found a document online on September 21st, 2017, emulating a Honeywell 6180 computer system. Somebody had already done this, apparently. It was a study done by the MITRE Corporation. And it was 39 pages, so really they're not emulating it, but they talked about what they thought the scope of writing an emulator was, and they underestimated badly. ISO result. Simple fix, install the change order. A couple years back, there was a leap second. The emulator crashed during the leap second. We were using a third-party library to do IPC communication, and it had an assert in it, checking the clock very carefully, and it died on the leap second jump due to timing considerations, and crashed the process. June 2014, I discovered a bug in Multics, minor bug that I found through code examination. I was tracking down a bug in the emulator, following some data moving through the Multics data structures. Looked up the structure declaration and counting bits to extract fields out of words. When analyzing the KST attributes declaration, I noticed that the declaration is not padded out to a word boundary, as was usual practice. And the last field in the declaration crossed the word boundary, which was quite atypical. The 39 highlighted there is a typo. It should be 30. Really minor. The structure is one word longer than it needed to be. On a lark, I wrote my analysis and put it out on the Multicians mailing list as a bug report, and this got the response.
I remember that posting.
The MCI board was the Multics Change Review Board. They reviewed and approved changes to Multics. They had a formal process of change, submittal, review, approval, audit, and installation. On July 6, 2017, a new MCRB composed of Multicians and emulator developers approved MCR 10021, fixing the issue. The fix was incorporated into Multics 12.6F. July 2015, I found a logic error in Multics program, acquire resource, used incorrect logic to check the error return status, causing a gibberish error message. I duly filed a bug report on the Multicians mailing list. Sometime in 2015, there was a discussion on the Multicians mailing list about the volume of emulator discussions on the list, and if moving technical discussions to a separate mailing list and inviting those Multicians who were interested in those details to join that list. This is a good idea. The Multicians list will be kept up to date on progress with detailed discussions and not of interest. During that discussion, the creator and maintainer of the Multicians website mailing list stated, I think the emulator development team are just as much Multicians as everybody else on the list and just as welcome. About that time, the names of the developers appeared on the website's list of Multicians. Thinking to myself, and I hope other developers, I was gobsmacked at that honor. I carry that title with great pride. The maintenance panel turned up out there, out in the front, out right by the front door. VCF West before last. I was demonstrating software. Dr. Moya from the LCM said, call me. Put me in contact with Stephen. He had purchased a front panel off the internet, and we wired the emulator into it. The lights and switches all function correctly. There were about 100 Multic sites. The emulator has, as of last July, 66 registered sites. So we're halfway there. Uh, 105,000 lines of code, release 12.6F. Things we're working on.
You see the robot thing. You want it just to show you that?
This was what we got. Classic computers, computers in lab. Supported maybe. Questions? Bravo!
Just for the record, Charles will be here at least another hour. As a operating systems programmer and sometimes hardware dabbler myself, I feel horrible yanking somebody from the stage. But I wanted to leave at least 10 minutes for questions. So, somebody please, let's start. Charles, I know you hate this stage. It's like you did fine. So, questions? Somebody, you must answer a question. Ask a question. Okay. If you can answer it too.
Hey Charles, thanks for all the help getting the Multics panel ready to get. It was so. When I bought that, I had the idea that someday somebody would write a Multics emulator and then we'd hook it up to it. And so it was great that we were able to bring that to fruition. And I was wondering, after this, would you be willing to show a small group of us the maintenance panel and give us a little tour of it? All right, thanks.
You mentioned like earlier versions of the hardware and also other operating systems like GCOS. Are there emulators for the older systems as well? And are the operating systems like GCOS working maybe? What's the state of that?
The audio for the recording.
GCOS is an active commercial product still and tightly controlled. It should run. There's no particular reason why it shouldn't run. There might be some fiddly low-level details in some of the configuration registers, but basically it's expecting to run the hardware in absolute mode all the time. It'll never switch to a pending mode. And the GCOS emulation code mostly works. So I would expect that to come right up. CP6 was the Xerox, CP5 was the Xerox operating system, CP6 was the port of that operating system to the hardware. Again, it should probably run, I am given to understand they rewrote the serial communications controller code. So it'll probably take a little while to get the dial-up lines working right. Because we don't do a low-level emulation of dial-up lines. We do a very high-level abstract. And the commands have probably changed. But can't find any copies of CP6.
What kind of modifications were required to get the physical front panel working with your simulator?
There's two versions of the hardware, the 6180 and the DPS8M. The second version was newer technology, newer semiconductor technology, and greater memory density, which allowed you to have fewer system controller units. So DPS8M has fewer connector ports to the system controller, and some odd changes here and there in some of the system control registers. We wrote the emulator for the DPS8M. The front panel is off the 6180. So vast majority of the data display was the same, but there was a handful of rework I needed to do to get a proper 6180 emulation mode. It probably took me about a week. One of the manuals we had was the Multics Differences Manual, and that specifically is detailing the differences between the 6180 and the DPS8M. So I actually had documentation for that step. We don't have any documentation for the maintenance manual. Many of the lights and switches were very obvious. Several others were kind of vague. One of the scrolls is entirely internal bus signals. K17512. What I did is I went through the code and every interesting control point, I turned on one of those lights. So the lights are not correct, but they behave visually similar for that particular control panel. The rest of the register bits, CPU state bits are all correct.
Other questions besides can I play with it?
Thank you. What a trip back. So I used a GCOS system at the University of Waterloo, which was a Honeywell 6660, and I think it got upgraded to a DPS8. And it was great hearing things like EIS and so forth that are 36-bit words and stuff. One of the curious things that would happen on that machine is if you had a pointer chain that had a cycle in it, which is a favorite interview question now, you would, after 2 milliseconds, you'd get a timeout. We called it a ZOP fault, a zero, I don't know what, zero page fault or something. Is that also present in this side of the world, in the Baltic side?
We catch it.
How do you do that in the emulator to get the timing right, et cetera?
1,024 times through the loop, I declare a timeout. So it won't be 2 milliseconds. It will be some amount of time. But if your indirect change is more than 1,024, then you're abusing the hardware and you deserve a timeout.
Best pun of the day. You deserve a timeout. Thank you. Any more questions? Charles will be here, and I believe he got arm twisted into a tour of the front panel. So, on that note, meet by the front panel. Any last words? Excuse me, you did great. Any last words, Hope? Okay. Thank you very much. Big round of applause for Charles.